Right, then I will start. So good morning, good afternoon, good evening for all the participants in our space webinar. Welcome to join us. So today we are really glad to invite it and honored to invite Prof. Xiaoxiang to give us a wonderful talk on data science in Earth observations. Before we start, let me give a brief introduction to Prof. Xiaoxiang, who is our speaker today. Prof. Xiaoxiang received the all of the bachelor, master, and doctor degrees in signal processing from TUM, Germany. And currently she is a professor of signal processing in Earth observations with TUM and also the German Aerospace Center, DLR. And also she is the head of the Department of EO Data Science, Earth Observation Center in Germany. And she's also the head of the Hormoth Young Investigators Group with the DLR and TUM. And she's currently coordinating the Munich Data Science Research School, TUM as well. Dr. Zhu is also a member of the Young Academy with the Berlin Brandenburg Academy of Science. And also, she's associate editor of IEEE Transactions on Geoscience and Remote Sensing. So without further ado, let me just pass the time to Prof. Xiaoxiang and as welcome her wonderful talk on data science in Earth observation.
Thanks a lot, Bihan, for the nice introduction. Thanks a lot for the great opportunity to share our work on data science in Earth observation. And as a starting point, I first want to show one video, because I guess for many of you probably don't know what Earth observation is actually about. So you see in the center, the Earth is rotating. We have Earth observation satellite, which is orbiting the Earth. And while the satellite is orbiting, Earth is also rotating. So in this manner, basically we can make measurements of the Earth's surface. And if we would steer into a certain position, then we can also get a very high resolution information of that area. So we are now living in the golden age of Earth observation, because this is how our PhD student having the lunch break. No, I'm just kidding. Simply because now Earth observation has entered the big data era. We have a lot of, and also increasing number of which is in the orbit. And to give you a European view, basically this is ESA's Earth observation missions. We have 3 branches, science, Copernicus, and meteorology. And among these 3, the game changer is the Copernicus program, which has its Sentinel satellite fleet. And they are basically orbiting the Earth, providing, let's say, information of the Earth surface on a weekly basis. And more importantly, it has this free and open data policy. So basically all data acquired by these satellites are free to everybody. And till today, roughly 30 petabytes of data has already been acquired and shared. So what do we use this data for? I'll give one example. So, you know, Arctic sea ice is a very important climate level. While sea ice is melting, it warms up the ocean, which will in turn also influence the ocean currents. However, in order to give a reliable statement about sea ice, it is not enough if we look into the past several months. Instead, we need to analyze data from past decades. In this case, is the last 40 years. Only with such data, we will be able to see whether the sea ice is retreating, to which extent, and from this, we can make a prognosis. Why do we need data science in Earth observation? And you can imagine, on the one hand, we have our observation systems, which are our satellites, are making measurements of the Earth surface. On the other hand, we have users. This could be scientists, decision makers, also industrial section. You can imagine what the satellite is measuring is not exactly what the user is actually need. Therefore, we have information retrieval as a very important part in the whole chain to turn basically the acquired satellite data to data research services and applications to different user domain. And of course, here, computational imaging, which is probably the main focus of this community, has become also crucial for Earth observation. So basically here is an selected important, let's say, competence we need if we want to master data science and AI in Earth observation. We need explorative signal processing methods to improve the information retrieval, because either you can try to get a better satellite in order to get, let's say, more accurate information, or in turn, we can try to improve the model-based retrieval methods. Of course, one is much more cheaper. Data fusion is a very important topic in our field. Because nowadays, if you want to use Earth observation satellite data for any type of application, you will have different, let's say, satellite data from diverse type of sensoric for your choice. It's definitely a wise idea to try to combine the complementary feature of different data and try to optimize the information retrieval process. And another very important topic is information mining. And nowadays, because we are all confronted with tens of petabytes of data, in order to actually figure out what are the interesting data, here information mining is very important. In particular, since all the labels are very important, you want to be able to efficiently detect changes or novelty in your data in an unsupervised or semi-supervised way. And another very important component is the machine learning and the deep learning. Because of the huge amount of data, more data-driven type of analytics are becoming always more important. And last but not least, we also have to take care of very practical things, which is big data management and high performance computing. So I just give one example of, let's say, deep learning. So now it's basically more or less an international hype. However, in Earth observation, if we want to apply deep learning methods for our applications, then it's very important to be well informed about the sensor characteristics and try to understand what actually make deep learning special for our applications. And based on this, we can develop architectures, prepare tailored training data sets for different applications. Here is just a simple overview of a small selection of our designed deep neural networks. We call it our deep net zoom. But today I will really not go to any, let's say, technical detail. Instead, I rather want to share one Earth observation data science story with you, which is global urban mapping. With Earth observation data, we are contributing to UN's Sustainable Development Goals. And for this particular story, we mostly look at number 1, zero poverty, and number 11, sustainable cities and communities. So I guess this is familiar to everybody. So we are living in an urban planet, no matter we like it. If you look at the population in billions evolving with the time, you will see there is a secret change in the history. In 2008, there are more people living in urban areas than in the rural areas. And this trend will continue. If you look at the data 2050, then there will be roughly 2 billion more people. They are virtually all living in the cities. And this is something probably not everybody know. So actually starting from 2014, for the first time in the IPCC report, there is actually a dedicated chapter on urban areas. This highlights actually the highly dense urban area are contributing to climate action. And this is another hint how important it is to look at these areas. And if you look at the geographic distribution of urbanization, So basically in this graph, if the color is more light, then urbanization is happening or will happen in the future. If it's a more dark blue color, then it's a more established part. So from this figure, you can easily see urban growth are happening mostly in developing areas like South America, Africa, Asia. And for these areas, actually, if urbanization is not very well controlled, it's too rapid, then it will introduce also societal problems. And I will give an example of Mumbai. 2 years ago, very big in the media, in Mumbai in the past decades, there were actually around 50,000 fires. And very sad is that almost up to 70% are caused by faulty wiring, really bad planning. And in order to, of course, improve the situation, we first need is to provide geo information. So basically, where are the buildings, where are the slums, how high are the buildings, how many people are living there. However, very, let's say, shocking effect is, for example, this is the city of Lagos, and it has a population of 21 million. But for such a city, we even don't have a 3D model. So actually what I want to say is the geoinformation we need to tackle this kind of societal challenges are not there. So there is a big gap in geoinformation and strategic decision making. This comes to our work. Basically, starting from 2016, we are trying to fuse about 10 petabyte data from satellite to social media and try to make a breakthrough in this direction. And what you see on the graph is basically a state of the art of global urban mapping, which is the global urban footprint. And this is the kind of information you can get on a global scale. It's nothing else but a binary mask of urban and non-urban in a resolution of 12 meter. This was the result in 2012. And of course, in the meantime, there are further development. For example, there are a world settlement layer, which not only gives this mask, but also how it evolves over time. But still, the information gap is very big. In our project, basically what we are trying to do is to deliver global, let's say 3D and 4D urban models on the individual building level. And we also try to figure out which type of building it is and try to provide a high resolution purple density map across the globe. And the idea is relatively straightforward. We are using radar satellite to get the building height, and we are using multispectral hyperspectral sensors to understand which kind of roof material is there. And more interestingly, we are combining social media images, for example, a ground view type of image, which are capturing the facade of the building. This tells much more about building functions than just a top view. And in addition, we are streaming anomalously tweets sent from certain geolocation, even though we don't know who is sending the message. But from the content, for example, if you see this example, I say I'm in the rooftop bar, then you know this is rather a commercial area. This helps us basically to get a clue which kind of building it is. And if we would have the building function like residential and also the 3D model like the building height, then basically we can do a transparent calculation about population according to the capacity. So this is the plan. And with a small difference is that we don't want to do this for one building. Instead, we want to do it for every building on the Earth. And this end up with 10 petabytes of data. As I was mentioning, what you see is a video of the German remote sensing data archive at the German Aerospace Center. And 10 petabyte data basically means 1/3 of the whole archive. Okay, today, I will show you some results we already achieved with signal processing machine learning methods. Basically, if we look at the current state of the art, We are now in an era we're all talking about open science and open data. If I talk about urban, then what will come to your mind is probably OpenStreetMap. Basically, the current situation is there is around 3 billion buildings in the world, and there are only slightly more than 300 million buildings, which is smaller than 12% of the whole. And among these, only 3% of the buildings have height information with big arrows, roughly 5 meters. So this will be around 0.5% of the whole building we have. So basically we are closing the gap. We want to get all building footprints with every building with a height assigned to it. So how do we basically get the building footprint? Before I start, I first want to show you a short video from Planet Lab. This is a new space company. They are basically launching hundreds of these small CubeSat satellites, and they are making, let's say, rapid mapping of the Earth surface in the resolution around 3 to 5 meters. Although the image quality is not comparable, of course, to the big machines we operating in the space agencies, but the good side is they are providing data on a daily basis. So every day you get a global coverage. And basically the first satellites is called doves are directly thrown out from the International Space Station. And this is a picture showing the CEO of Planet Lab, William Marshall, with such a satellite in his hand, such that you can get an impression how big the satellite is. So how do we actually get building footprint from this type of data? So here we are using we call graph convolutional recurrent neural networks tailored to this task. And for generated the training data, we have the pairs for satellite image and these building footprints from 74 cities. And for according to the methods, we're using convolutional networks to extract the high-level features, then use graph to connect the contextual information. And then we're using a recurrent module to progressively improve the results. And now we are coming back to Lagos. This is the planet imagery of Lagos. It's a very, very big city. And today, at least we are able to provide already the building footprint, which you see is in black. And if you we zoom into a certain area, then you can see this is actually the image quality we're able to get. You see that with 3 to 4 meter resolution, of course, it's good, but it's not perfect for the building footprint extraction. And this view graph shows you the inference results from our graph convolutional recurrent neural network. And if we improve the network with multitask learning, we can also get building instances. So here, different color stands for the, let's say, the pixels for different buildings. And you can see these tiny buildings can be very well separated, but you also see for sometimes it fails. For example, this red cluster you see here, this is actually slums, so very densely packed areas. So this also gives us a hint how to identify slums in basically this kind of relatively coarse resolution imagery. And this is, let's say, a direct inference we do in the past days. You know, there is a tragedy happening in Beirut, Lebanon. There's a very big explosion. And in this work example, what we do is we inference the building footprint from planet imagery before and after the disaster. And basically by simply compare the building footprint we extracted, we are able to identify where there is a building damages from this explosion. But of course, since the satellite it has a God view, only looking on the top, you basically see only the changes where the building are distorted from the shape. And they're actually have a much larger influence where the facades glasses are broken. Unfortunately, this will not be able to be detected with top view satellite image. And this is basically compared to the ground truth data, which is announced by the ZKI for the crisis management. And you will see that even though with the pre-trained model we used before with 74 cities we have chosen, it gives quite good performance to identify the damages, which is marked red in this image and in green in our results. Okay, this is how we do the building footprint. The current status is we are now finished with the downloading of Africa data, and we probably will get all the beautiful footprints in Africa prepared in the end of September this year. And how about building in 3D? So for this part, we are switching to a different satellite. This satellite is called Terasa X, and this is a German X-band radar satellite launched in 2007, but it's still in a healthy status. It's still serving us. Very good proof of German engineering. And the radar satellite works in the following. So it sends a package of waves to the Earth surface and then records the reflected echo. So basically in the radar image, we are recording two things. One is the reflectivity, which is how strong is the reflected echo. And then most precious information is the phase, basically tells the distance from the satellite to the Earth surface. And this satellite is a mission we are very proud of, because still today, it is still the, let's say, a civil satellite, which is providing so far the highest spatial resolution, which is in ½ meter. And if you have never seen a radar satellite image before, this is how the capital city of Germany looks like, the city of Berlin. For those who have been to Berlin before, you basically can identify here is Potsdamer Platz, the only high-rise area of Berlin. And here is where Angela Merkel is working. And if you look at here, basically you see the Berlin railway station. And here you see the Siegersäule is the status. And although with very high resolution, you see a lot of details. If you pay attention to this image, you will see all the buildings are somehow falling down to the ground. It's like you put a 3D city into an oven, then they're collapsing to the ground. And this is mostly because radar is looking to the side. It has a side lookometry. So if you look at this image, assume satellite is at a certain position, basically reflected echo from all objects which are sharing the same distance to the sensor, they have been mapped into 1 pixel. So this is why this building somehow looks like a clip to the ground. And in order to do a 3D reconstruction, then it's obviously a 2D image is not enough. The technique we do is called radar tomography. You can also call it X-ray of the Earth. The idea is simply every 11 days, the satellite will pass over the same area, taking another image from a slightly different position. And we repeat this process, and slowly we will be able to get many images taking slightly different position. And if you are more from the signal processing side, then you know a far field antenna acts like kind of a free transform. And if you look at each of these images, assume this gamma is the reflectivity we want to reconstruct along the this kind of what we call elevation direction. And basically each of this image could be considered as kind of a sampled Fourier transform of this reflectivity function. And the sample position depends on the sensor position, of course. So this basically says radar tomography is actually a spectral estimation problem. And but we of course have special things to consider. For example, the sampling due to orbit uncertainty is not regularly sampled. And each image are very expensive, then we don't have really a lot of samples. Therefore, we have a small n. And also, if you think about, we need 30 images to do a reconstruction, they are acquired within a year. On the one hand, this gives us the opportunity to monitor the object. On the other hand, then motion must be considered. This is the special considerations we do. But we do have a very elegant tools we could use. For those who is not familiar with basically satellite and so on, you can refer to CT. The only difference is we are now not doing a 360 scan. Instead, we are doing a scan with a very small angular diversity. And we are also not recording the transparency. Instead, we are recording the reflectivity. So this is the comparison to CT. And the nice property I mentioned before, which we are actually profit a lot from, is sparsity. So eventually what we want to do is to reconstruct a 2D surface in a full 3D space. And if you zoom into one of these pixels, even though you want to reconstruct a continuous elevation profile along S, but since there are only very few number of objects which are scattering back, so you can assume sparsity here, and you can also use sparsity as prior group sparsity and all this kind of regularization. And the good thing, if we use this, is super resolution. So this is an example where is a simulation example to show you the what we mean super resolution in our sense. So if you see that radar looking to the side, as I said, because of these reflected signals from the rough surface and also from the balcony, they are somehow fall into 1 pixel. And if you use a standard map estimator to do the spectral estimation, you basically cannot distinguish two scatters, we call scatters. So it's really the source. If they are somehow within one ready resolution unit. But if we can somehow apply sparsity, enforce sparsity in the, let's say, retrieval process, then use the algorithm we call limit. So this is nothing else than a sparsity reconstruction-based methods. Then you will see that we are able to separate the two sources very well. So basically, according to our extensive experiment with the interesting parameter range of a radar satellite, we're able to achieve a super resolution factor or between 1.5 to 20. So which is depending, of course, the number of acquisitions we have, as well as the signal to noise ratio we have. And now coming back to the Berlin case, and here we need actually a supercomputer because we do actually previously mentioned sparse reconstruction for each pixel. And this would mean solving an optimization problem with a matrix dimension of about 100 times 1 million for each pixel. So if we process Berlin, then this means we have 10,000 pixel times 6,000 pixel. So this is basically the computation we need to do. And with this, we are getting a lot of support from our Leibniz Computing Center. And basically, after you do the retrieval, you finally see a tomographic city tour of Berlin. Color stands for the height. And basically from blue to red is lower to higher height. And you can see clearly the Berlin Central Railway Station. And this was the status I showed before. And if you look along the streets, you see this kind of regular patterns. These are actually lampposts along the roads. So for the city of Berlin, we are getting 1 million point per kilometer square for these 3D point clouds. And what is more exciting is that behind each of these points, because radar is measuring the change in the fraction of the wavelengths. X band, which means we have a wavelength of 3.1 centimeter. If the position of the ground object moves for a fraction of this wavelength, we're able to see with the radar. From the signal processing point of view, we're just extending a one-dimensional spectral estimation problem to higher dimensional spectral estimation problem. And after you do this, then basically you will be able to see this kind of information for every pixel. This is upper is the Berlin Central Railway Station in which bottom you see how the building is breathing according to the temperature change from summer to winter. Of course, in order to make the so-called deformation visible, the deformation is exaggerated for thousands of times. But if you look at the color bar, basically this kind of deformation is in the scale of around 1 centimeter. And if you look, for example, the main building of the Berlin, it's rather this type of, let's say, expanding kind of deformation. And if you look at the different railway sections, because there are gaps built for the thermal dilation, you see rather this kind of horizontal type of movement. And basically, we are able to get this information for every of the points I showed you before. And for thermal dilation, it's not dangerous. But if we have any kind of seismic activities like in California or in Japan, then this kind of information is very crucial for infrastructure monitoring. Or if there would be any tunnel built in the city, you want to know how stable actually the infrastructures are, then you can use this technique. Well, so if globally we would have this type of data, we would have been done already with the 3D reconstruction. But unfortunately, if we talk about a global scale, then we have data which is in worse quality. And this is the 10x mission. So basically you see how the mission is covering the whole Earth in a year. And basically in terms of technical specifications, switching to this mission means we are changing from, let's say, image resolution from 0.5 meter to 3-4 meters. And also the number of images, we don't have 30 images per city. Instead, we probably have up to 5-6 per image, as you see from this animation. To take one global coverage, we need a year. So therefore, we have developed a data science approach for this, using the X-ray of the Earth and using this relatively coarser resolution data, we will be able to estimate building height very precisely. And we combine with previously what I introduced. We use planet data and overtrained deep learning model to predict the building shapes. And if we combine these two information together, then basically this is the first impression of the global 3D urban models we will achieve globally in about 1.5 years. And this is the real data example of Munich city and the characteristics for terrain height plus building height. We did a detailed comparison with a very precise LiDAR DEM. And in the end, comparing 30,000 buildings tells us the building height estimation is better than 2 meters. And this kind of model, we basically can expect to have it everywhere, also in any Africa cities in around 1.5 years. And currently we are proceeding with the global processing. Okay, this is about how do we get building in 2D and 3D. And now let's talk about settlement type. This means, is this a commercial, residential, which kind of building it is? But there's no one step to Rome because actually the building types are very, how they appear in satellite image is very cultural dependent. For example, slums in South America would be these lightweight, low-rise buildings. But if you go to Paris, they're high-rise buildings. And therefore, as a step towards it, we're more look at the morphological structure of urban areas. And we are basically mapping this with the so-called local climate zones classification schema. And it's basically originated from urban climate society. It describes, for example, how compact are urban areas, how dense, how high are the buildings, and how many percentage of green are there. So, but this is actually a very good, let's say, step towards building functions. Because if you look at class number 1, which is high-rise compact, if you look at the Vancouver example, basically here is the high-rise compact. Basically, this is related to the city center area. And if you look at the 7th class, which is lightweight low-rise, then this automatically probably brings you to this kind of slums, how we understand slums. And of course, in order to do a global local climate zones classification, we use more, let's say, deep learning type of methods. First step towards this is to generate a representative training data. And for this particular, let's say, problem, we have been selecting 42 cities across the globe, plus 10 additional cities to add, let's say, imbalanced samples to make it more balanced. And in the end, we end up more than 400,000 pairs of Sentinel-1, which is radar. Sentinel-2 is multispectral image patches with a label. So this is upper row basically shows how these areas look like in a satellite image. And on top of that, we want to basically also control the quality. Therefore, after the hand labeling, we also vote for each of these labels to get a confidence score. So this is basically the matrix showing here. So this tells you how confident, how good is the labeling quality, or actually this also reflects how humans can well recognize the difference between different, let's say, local climate zones. And we are, of course, using different satellite data. Here is just example methods we use for Sentinel-2 data. Since we use Sentinel-2 seasonal data, we first use a convolutional network to extract the feature from this data. And here we use ResNet as backbone. And afterwards, we stacked with kind of recurrent module. In this case is LSTM. In the end, we will be able to get the local climate zones map. And this is how the global urban local climate zones looks like. Of course, the more interesting part is the reddish part. This is the urbanized area. And basically to show you one example, so this is how on the right, the local climate zones map we achieved compared to the left, the GOOF, global urban footprint, the state-of-the-art methods. So you can see there are much more semantic and the morphological structure information of the urban patterns are available. So let's looking a little bit closer to these results. For example, we did let's say, proportion analysis of man-made structures, which is the 1 to 10 classes. And this is basically the pie chart for how it's distributed. And in addition, we combine this distribution with population data, basically analyze preliminary, that's a typo, preliminary analysis on 1,692 cities, which is according to the UN, cities with population more than 300,000. It quantifies a global inequality problem. So basically, there are around 40 area. There are 40% of the area of these urban areas. They are compact areas or light or large low-rise areas. They accommodate roughly 60% of the total population. And then there are 30% area of sparsely built. This is more houses. They accommodate only 10% of the total population. So basically, this is just a preliminary analysis we could do with this type of data because such kind of information was not available before. But this raise again the societal problems we have. And another part is tweeting for social good. So I guess probably quite of the participants in the audience, you're also tweeting. How could you do this for social good? And as I was mentioning, we are trying to combine remote sensing data with social media text messages to get the building functions. So if I give you one example, so this is basically tweets of residential, non-residential, and the mixed-use area. On the left-hand side, you basically see the area, and in the middle, you see some example tweets. On the right, we don't do anything else but a 724 chart. So how the tweets are distributed one day within 24 hours, and how they are distributing among the week, the 7 days in a week. You already see different patterns. So if you look at the top, this is more the residential area. Basically, you see people are tweeting much less in residential area, but you can also see that the yellow colored areas, they're more happily in the dinner time from 5 p.m. to 8 p.m. And if you look at the mixed use, these are more shopping malls and all this kind of commercialized area. Then you see a typical Munich phenomena. So in Munich, all the shops open at 7 a.m. and close at mostly at 8 p.m. So basically, you see a very good, let's say, correlation with the opening hours. So with this, you can already get a hint about building functions. Moreover, you can look into the content, even though we don't know who are sending the messages, but you can imagine people are talking about different topics at different occasions. Even though for job, this is a very popular topic everywhere. And if you are at working place, probably you are more talking about the working content. And if you are at home, it's rather more related to your emotions, how you feel about the job. So from this, you can basically tell the functions of the buildings. So this is basically the pipeline we have. We can combine the spatial temporal features, how tweets are sent around, and also the topics. So which topics are discussed. We can fuse these two information, and here is the preliminary results about building function prediction. And what you see on the screen are OpenStreetMap ground truth. The cyan is the residential area. The purple is the commercial area, and this is what you could predict from tweets. I go first and the back, then you can see basically the residential, you get much less information density because not everybody is tweeting, but you can also see the non-trivial pattern of commercial areas are very well captured. And Twitter data, if you register for API, basically you can stream global tweets. They will provide you 1% randomly selected tweets. And so far we have been streaming more than 300 million precisely geolocated tweets. And of course, to get a model that are basically can be scaled up, it's also a big topic. For example, we need to dealing with multilingual word embedding. We need to figure out the, let's say, the local bias in the tweet content and so on. There are many issues to be addressed. Now, finally, I want to share you with our vision. Basically, in 2022, we want to be able to deliver a first and unique global and consistent 3D, 4D spatial data sets on the urban morphology. This means if you go to any city, including the Mumbai I showed you before, we will be able to go beyond state of the art, which is this binary mask of urban and non-urban. For example, we will know where the slums actually is. If the authority want to improve, let's say, planning of certain slums, we can also get appropriate 3D model of the area as well as population density of the area. So finally, the data we generate for a global urban mapping will be open because we want to actually have a better understanding and boost research on global change process of urbanization. And we believe this kind of a unique data set is very important for stakeholders like UN to make the strategical decisions. And more important, as a data scientist, this is our way we want to offer a helping hand to address the poverty problem, because only with information, then you can start doing something. And here is basically the whole team. We are working on this global urban mapping project. And of course, with not their contribution, we could not be at the place we are today. And we also get a lot of support from our German computing center with today probably 50 million CPU hours with a lot of storage. And well, so this is just an example how basically data science in Earth observation is supporting global urbanization, but actually data science is going far beyond this topic. And at DR, we are research and develop solutions for major challenges in these areas like Earth system science, global change research. Meteorology is a classic field we contribute. As I mentioned, or also give example, we provide indicators to how UN's SDGs has been implemented, and down to very practical things if we work with very high resolution like security, mobility, resource management, and city planning. Well, so this all from my side. Basically, here are related information, for example, to the global urban mapping project, SOTUSAT. And if you're generally interested in the methods we develop, then in the middle is our lab page. And on the right, it's a new lab we're starting more focus on AI for EO research. And there, very important topic, I guess it will be asked by the audience also, the ethical guidance we need to publish such data will, for example, be addressed in this future AI for EO lab. Thanks a lot.
Thank you so much. Thank you, Prof. Xiaoxiang for the wonderful talk. And I think we do receive many questions from the audience, as you can see in the Q&A list. But actually, before moving to the question from the audience, I just want to make sure. I just want to check: is there any question coming from the panelists? Sai, John, or Jane? Do you have any specific question for Prof. Xiaoxiang? Okay, if not, maybe I can start with some questions regarding the talk. Because just one quick question, because Prof. Xiaoxiang, you mentioned a lot of interesting applications by fusing those multimodality data, like you mentioned about the getting some information from Twitter, and also you have some LSTM type of network to extract the spatial temporal data, by capturing different snapshots of the SAR images. I'm just wondering, is there more details about how you actually design those network to handle this specific task? Because I think this is really of really broad interest for even other imaging problems or computer vision problems as well. I'm just curious, is there anything special for this remote sensing task or application specifically?
Yeah, so I mean, firstly, of course, there is no general answer to this question when you want to fuse different modality. I mean, our general experience tells if you try to fuse the data from the data level, feature level, or decision level, usually since the modality of satellite data are too different from each other, then fusion in the later stage, feature level or decision level works in generally better. But of course, this is really depends on the particular application we are talking about, right? If you are rather talking about so to say, to get a time series data from the sensor and try to basically get changes from this type of data, probably your choice will be different. And for those who is actually also in the audience who want to know more about how we do the data fusion, also the details about the deep Zoom are presented, you are very welcome to go to the second link I provided here. And if you go to the publication site, then for most of this, we are providing links to the paper as well as to the code you can play with.
Thank you. So yeah, like Prof. Xiaoxiang just mentioned, for those people who are interested of more details about those technical details of the works, Prof. Zhu mentioned, you can maybe scan the QR code and check out those details in the links, and you can maybe find out more. Thank you. Maybe now we can move to the question from the audience. We do receive a lot. The first one is actually coming from Shiraz. So Shiraz, do you want to like ask live? I can try to unmute you if you want. Let me see, ask to unmute. Shiraz, if you have your mic, you can actually unmute and ask question live. Otherwise, I will just read the question for you. Okay. So yeah, so I think the first question Shiraz asked was, so just try to see if you can provide a link to your deep nets rule. But I think that one you already mentioned, right? There's some details in this links. Or is there anything you want to add, Prof?
Yeah, so I mean, as I said, papers, codes, you can try to find it in our lab page publication site. In addition, we also have our group GitHub, which I don't provide it today, but if you basically try to check our website in the next days, we will make it public, because this is something we organized roughly 2 weeks ago. So it will be brought live very soon.
Great, thank you. And then the next question also from Shiraz is, he's asking, what is the data that the project seeks to acquire with respect to the buildings, and how do the current data handling legislations view this method of data acquisition? Prof, you want to quickly comment on this? Oh, you can actually view the question by clicking the Q&A button at the bottom. There's a and then you can see all the questions actually.
I am not 100% sure if I understand the question correctly. Shiraz, could you please probably reformulate exactly what do you mean by, for example, data acquisition?
So yeah, sure. So yeah, if you're still online, you can try to maybe like rephrase your question, or you can choose to ask live. I tried to unmute you, but didn't see any response. But anyway, we can move to the next one, and yeah, if we hear from Shiraz, we can get back to this.
Bihan, I think Shiraz mentioned that he has issues with his microphone, so.
Oh, okay.
Okay. Yeah, so I have maybe you can comment what exactly you mean by data acquisition. I'm not sure if I explained clearly. So we are basically satellite data from different sensors, and as well as we are streaming social media data, which are usually together with the geotech. And those are the open data basically published under Creative Commons license. Is your question more related to privacy, or what is the point? So if you could just type in the Q&A chat, that would be good.
Yes, I think we can wait for some updates from Shiraz later. But yeah, I mean, meanwhile, we can maybe move on to the next question since there are more coming. So the next one is coming from Sanderesh, but seems like he's offline now. I cannot find his name here. But anyway, so the question is to ask, how do you actually get the ground truth segmentations? I guess he's referring to the annotations, right? Where do you get the annotation for your segmentation task to train those network?
Yeah, so for the beautiful part, using OpenStreetMap data as let's say a ground truth, and then we do a manual examination of all the patches which we use for training. So this is how we are doing it. And for this, the other thing I mentioned, for the local climate zones classification, it's really based on hand-labeled annotated data. And there are actually community effort, it's called UDAP, where everybody try to contribute to label some cities according to the local climate zone schema. But the problem is this is a very, let's say, abstract classification schema, and the quality cannot be controlled if it's contributed by different user, and also actually the level of detail people different. In the end, since we want to provide a high quality global map, we had to do, let's say, basically hand labeling by ourselves. So it's done by 15 scientists, including myself, for a month. We are labeling basically different classes. And since this is probably one-time effort, we also try to get 10 people give independent vote for each areas, such that we could also get a confidence score for the labeling process. I hope this answers your question.
Yes, I think that's a I mean, really good answer. I think, but seems to me a lot of effort, right, to annotate the large scale data. All right, so then let's move to the next. Yeah, so yeah, because I guess for a remote sensing area, the data scale should be much larger than the regular images we're dealing with in computer vision and image processing. So yeah, really appreciate the efforts. And then let's move to the next question, and this is from Han Zhao. And I think the question is about the graph convolutional neural network. I think is using one of the work Prof you mentioned. So he's asking how is the adjacency matrix defined, which is very specific. So Han Zhao, you want to ask, anything you want to comment? I actually unmute you so you can talk, or otherwise, Prof, you can comment on his question.
Yeah. So I mean. In this work particularly, we first have convolutional blocks to extract the high-level features. And afterwards, in order to get a better information propagation, we just define the adjacency matrix to be the pixel with all the direct labels. This is how it's defined. Of course, using basically GCN to the somewhat since there is a defined basically labelhood, the way to, of course, to make it more efficient. This would require a bit massage the current framework we have, but this is definitely one point one could try to improve. I hope this answers your question.
Yeah. I mean, in case you guys have other comments or follow-up questions, feel free to leave in the Q&A. And then if not, let's move to the next one. Also from Shiraj, he's asking like to geotag the tweets to the locations they are, originating from. Will this have any legal implication? So, Prof, you want to comment on this?
Yeah, sure. So I mean, using tweeting data. Twitter data, firstly, because we are using the official API from Twitter, and we also don't have the, let's say, user ID of the data, and all this data which we can stream is published under the Creative Commons license. From this point of view, I would say that's okay. But obviously, if there would be a single tweeter from a residential area, you have a geotag, and basically it's easy to identify who it is. I do see there are ethical problems there. This was actually also one of the reasons now why in the future AI for your lab, where you see on the screen, we try to basically put ethical guidance as the very important topic for EO, also particularly for AI for EO. So this means we want a really transparent guidance, how we can try to avoid bias in the data, not that we are give benefit to any social group when we try to provide global geo information, and also about privacy, in which way we're able to share information that could not be misused, and also how could we taking care of general ethical issues in AI-based methods.
Mm-hmm. Thank you. So then the next question is coming from Alan. So similarly, I unmute Alan. If you want to comment on something, you can talk live. So the question is actually using these satellites and methods, what is the resulting time resolution to be able to see change in urban map and buildings?
Mm-hmm. Yeah, so this is, I would say, depending on the particular, let's say, change scenario. If we are talking about long-term deformation caused by ground movement, caused by seismic movement also, then I think if you would have data on about monthly basis, that would be good. But if you are talking about crisis management, then of course this kind of daily repeating data from revisited data from planet, this is very important. But if you are generally talking about land use, land cover change, then I guess what Sentinel is offering with the weekly time difference should be actually enough. You will be able to see phenology, you will be able to see city changes caused by the new construction or whatever. So I'm sorry to answer your question with it depends, but in actual situation, it depends.
Yes, thank you. Okay, so Anna, you have anything to add? I saw you unmute your mic.
I was just wondering, with the satellite data that you started off listing, you know, the first satellite had daily coverage, and then, of course, with the X-ray satellite, the processing had a much longer time period. So with these specific data sets, how what's the time resolution you can see as far as building changes, not from a crisis, but from an evolution, like if somebody builds a new building or somebody tears down a building or changes from slum to high rise, for instance, what time resolution can you observe with these satellites?
Mm-hmm. Okay, so I think we should not confuse two things, change and the deformation. So if I talk about deformation, then I'm talking about the same infrastructure, but because of ground movement or because of seismic movement, then it has a very small, let's say, deformation during the time. So this is very important if you want to monitor the healthy status of infrastructure. Change is, however, larger scale things. So if you build up a new house, if you try to figure out, let's say, undocumented buildings, this is usually not done with the TerraX satellite I was mentioning. For that one, you are using radar. This is a kind of a coherent method. Then you actually rely on there's no big change happening. This is the key for you to see coherence waves and being able to compare the phases to see how they are moving the positions. So I just want to make it clear. And as I said, for the deformation, since we are interested in long-term stuff, then with 10 days or every month interval, that's quite okay. And if it's changed, then I think at the moment, if you do, let's say, want a general methods with planet imagery probably the best has with the new spectral bands. So every day you get an image. I think this is far from enough for you to figure out all the possible changes. But this is not a radar satellite. Instead, it's an optical satellite.
Thank you.
Thank you, Adam, for the nice question. Thank you, Prof. Okay, so then maybe we can move to the next one. This is coming from Andre, if I pronounce correctly. So he's asking, could you use a real estate market data to find building plans?
Yeah, so that's an interesting perspective to this problem. Of course, locally, if you want to get, let's say, information about buildings, you might have, let's say, data source from real estate or authorities. But the framework I'm presenting today, which is actually trying to closing possible information gaps, because even though let's give an example. I'm living in Munich. For such a city, you would have not a problem at all to find the information I was presenting today, to get the building shapes, to get the building heights. And our project, however, more focused on consistent data across the globe. Even though we don't put any priorities, in the end, it's of course much more benefit for developing areas where you don't have such data. I'm not sure if this answers your question.
Yeah, also, I actually unmute Andre. So if you have anything to comment, you can feel free to talk. Or you have any follow-up question. Okay,
normally, to rise a building, you need a permit. And all the permits are recorded. And to spend a year of electricity to processing the data, probably for one city database will take just a week.
Mm-hmm. Acoustically, I could not understand so well. Maybe Bihan, could you explain the question for me?
Yeah, I mean, I also didn't get it. So, I mean, I just wondering if that's a follow-up question, or Andrew is trying to explain his previous question. But anyway, Andre, so I mean, we can move on now. But if you have any follow-up question, you can feel free to just leave it as another question in the Q&A, perhaps. Yeah, so it's better to maybe write it down so we can follow up.
Yeah,
okay. So yeah.
I'm just afraid it's because of my acoustic quality that I could not hear clearly what Andre is talking about. You're talking about 3 cities, half a day to get a city model or something like this. I only could extrapolate a bit, but I really cannot get the detailed question. Could you try to rephrase it or try to speak slowly such that I can understand you?
Yeah, I think I have a similar issue. I cannot hear very clearly, maybe because the network problem. But Andrew, I mean, feel free to maybe write it down, like Prof. Zhu mentioned. Maybe that's better for us to communicate. All right, so yeah, I mean, so given the limited time, so yeah, let's move on. Well, the next one is from Said, but I think that's not a question. He's just to say this is a really nice talk. Thank you.
Thank you.
Then the next one is from Ray. He's asking, what is the granularity in the natural roof classes? So can one tell a canvas, a straw, or wood roofs apart? And can one see, yeah, so can one see igloos?
Natural, well, so I mean, about the roof material. So basically, it depends on the spectral resolution we could have. So I mean, with let's say Sentinel-2 type of satellite, where we have slightly more than 10 spectral bands, probably it's possible to tell the difference of several major class of roof materials. But of course, everything improves if the spectral resolution improves. If you would have a hyperspectral sensor with about 200 bands, then basically you could tell actually a lot of more detail about the material, simply relying on that different material are giving more different reflectance to the sun illumination. So this is the things we rely on. And I hope this answers your question.
Mm-hmm. Yeah, I think we it's better we move quickly, but yeah. So, but anyway, so if there's any comment you want to leave, you can kind of follow up. So we can maybe skip the some kind of discussion for this kind of questions, and then to kind of facilitate the discussion, maybe we can leave the question by rating. That's maybe more effective. Okay, so let's move to the next one. So I think the question is saying, instead of using satellite images, well, you consider also use images from drone cameras. That's an interesting one.
Yeah, sure. I mean, we do not in this project, but in generally in our machine learning for Earth observation research, we use drone images, also drone videos to do different things like detect the cars, counting the cars, basically track the cars if we have videos, also detect events if there would be a fire happening, if there's a traffic jam or something like this. This is of course a super interesting and increasingly relevant data source for Earth observation. But for this very project, we are not using drones simply because we are aiming at quality controlled, consistent global data. Therefore, we are very much limited somehow to the availability of the data. If they are not globally or large scale available, basically we could not include in this very project. But yes, it's a very interesting data source we are researching on.
Mm-hmm. Then the next question is coming from Saeed as well. So he's asking, how can this be used to predict the population flow and the change in the climate and food status to ensure sufficient amenities can be allocated to that urban area?
Mm-hmm. Yeah, that's a super interesting and a relevant question. And this is the one to head to. So we as Earth observation scientists, what we could do is we turn the data acquired by satellite or we stream from social media, which is open data, to geoinformation, and how different communities use this open data for different applications. This is exactly what we want to see. So however, for us, we rather care, we get this information in a quality controlled way and make it openly accessible to the community. And once this is done, we welcome all possible, let's say, usage of the data, of course.
Mm-hmm. Thank you. Here's another question from Shraf, actually. He's asking whether there was any ethical clearance done with regard to the data acquired for this project.
Mm-hmm. Yeah, so things actually accept the Creative Commons license, which we actually choose data for social media platform. All other data are from satellite, they are civil Earth observation satellite. There is a law about basically satellite data, which resolution it can go, and so on. So we are working under this umbrella, and therefore, actually, this thing is already previously, let's say, cleared before we actually start to work with the data. So this is quite organized.
Mm-hmm. Thank you. And then the next question. the floor plans from cities such as Lagos and Mumbai.
Yeah, so I lost the connection for a while, but I guess I can read it, right?
Oh yeah, sure. Yeah, you can see the question from the Q&A. It should be the very first one.
Floor plans, are you basically meaning how many floors individual building has?
I think
okay.
so, yeah.
If this is the question, then basically we are providing this information in two folds. Firstly, for the LCZ classification, it has a class which is high rise, middle rise, and the low rise. And how this is defined is according to the number of floors it has. So this is the first information you could get. And the other thing is from the Tunnel X radar satellite reconstruction, we are able to get a building height with currently after validation with accuracy in 2 meters. Then basically you can calculate the floors according to your model. But of course, how good your model is, we cannot tell, right?
Oh, thank you. And then the next question is also from Ray, and he's asking, do roofs need to be dry to be properly classified?
That's a super interesting question. So, I mean, in reality, we don't wait until the roof to be dry, then we take the images. Instead, the satellite will fly over this area and it takes images. Instead, what we need to deal with is the spectral diversity. So variability, what we call. So basically, even so for the same type of material, depending on the weather, depending on the illumination angle, depending on the topography, it will show similar spectra, but they're not identically the same. So how to address spectral variability is actually a very well established research topic in remote sensing, and we are, for example, building up statistical models on top of that, or we try to basically use robust estimation frameworks in order to get a good, let's say, percentage estimation. There are a lot of, let's say, techniques for these purposes.
Thank you. Okay, so then here comes maybe the last question for you, Prof. And this is a question from Andre again. He's asking, to raise a building, a permit is required. To process a database will take a week instead of years of supercomputer.
Okay. I get your question. So we are again talking about different things. So if it's really just about building, let's say, footprint extraction to figure out where there's a building or not, and try to compare, is there any change of buildings? And for example, if we do inference for the whole Africa, it probably take us 2 weeks. So it's not that we need to wait for weeks of supercomputing in order to get this kind of information. And again, the deformation is a different story. It's rather related to the secret of buildings, how it undergoes very small changes. And for this, if you would need to marry it with GPS, for the Berlin city, you would need, for example, in that case, 120 million GPS stations, you know, to get this small movement. And instead, we are now trying to use satellite to do this, which can provide actually very large coverage at the same time, and you will be able to see a very homogeneous information content everywhere. You don't miss any point. This is the advantage of the satellite-based deformation monitoring.
Thank you. All right, so I think that's the, I can take the last two. So first, I think Richard, he says it's a really great talk. He enjoyed it. So thank you. Thank you for the nice work. And another question from Pramad. He's asking, will we get a link to watch the program again? So the answer is yes. The whole webinar, I mean, currently is actually broadcasting YouTube. And later, maybe like tomorrow, I'm going to update YouTube link as well. So you can also like replay it whenever you want to watch the whole webinar again. So yeah, so please check out our homepage to find the link, and all the updates will be there. So so then that's it for our today's webinar. Again, thank you so much, Prof. Xiaoxiang, for giving us this wonderful talk. Thank you so much. And also thank all the attendees to joining us within the hour. And also, again, so this webinar will be bi-weekly. So the next webinar will happen 2 weeks from now. And let me just quickly advertise the talk will be, the speaker will be our one of the organizers, Sai Prasad Ravishankar. And please stay tuned and look forward to see all of you 2 weeks from now. Thank you.
Thank you.
Thank you. So yeah, so thank you, Prof. Chu. So that will be the end of the talk today. Thank you so much. Okay,
Thanks
so
again
bye-bye,
for the
guys.
nice opportunity. Ciao.
Thank you.